Hi, this is Prasad Acharya. In this video, I will explain about our data science programming project, Sedan vs SUV classification using deep learning models. Car classification is considered important in the automotive industry. However, classifying cars manually can be very time consuming and expensive, especially when there are millions of images, and therefore automating this process using computer vision can be very useful. The aim of the image classification is to categorize all pixels in an image into one or more classes. This classifier can have various useful applications in the automotive industry, including car wash businesses where classifiers can be used for price automation, car rentals where classifiers can be used for fleet and inventory management, and in car sales websites as a data quality assurance for their body type filter. Our final dataset consists of 2060 images in total for both SUVs and sedans, 1030 images of each class. The images collected were two-dimensional in shape, colored and with different sizes. We also made sure to include at least 10 different makes and models for each class to create well-represented classes. Images for the vehicles were collected from different sources, including Google Images, Bing Search and Kaggle. We downloaded some of the images manually and some of the images downloaded using code. In our data collection process, we made sure to include variety of vehicles for both the classes. We downloaded the images with different colors, different angles and different backgrounds. We followed different pre-processing techniques to prepare image data. Image cleaning was necessary because the acquired images came from different sources, were messy and included some irrelevant ones. Before modeling, we cleaned them up and filtered out the bad quality images manually to reduce the complexity and increase the accuracy of the applied algorithm. These clean images were imported into the environment by looping through images in each folder in the specified path using os.listDiv function. Then both the SUV and sedan images were combined into one object called allCars and shuffled before training. For class labeling, we defined a function that loops through images in each path and assigned class labels. An if statement was used to assign 0 to sedan cars and 1 to SUVs. Normalizing the data is very useful when building deep learning models because it makes the neural nets to learn and converge faster. In our case, each element in an image represented a pixel value from 0 to 255. Normalizing the input values for the pixel was achieved using image data generator function by dividing each of the pixel values by 255 to produce a value between 0 and 1. The images we downloaded varied in sizes. Therefore, we had to resize all the images into same size before modeling. We used the CV2 package to resize our images. We tried different resizing dimension and explored the different models result accordingly. Grayscale images reduce computation complexity and prevents model from learning the unnecessary information from the images. Since in our case, color was not necessary to classify the images, we experimented with both color and grayscale images when modeling and compared our results. We tried different train test and train validation data splits to compare our model results. Our splits were stratified on our target variable. Another significant preprocessing method carried before modeling was data augmentation using image data generator. Data augmentation refers to applying different transformations like rotations, shift, zoom, and flip to existing images in our dataset to improve model generalization. The model building and tuning process was carried out in an iterative fashion to experiment with different model architectures, hyperparameters, and image formats in order to achieve the highest accuracy possible. The initial set of models were built using the MLP package as this was the simplest model that could tackle a complex task such as image classification, especially considering the high similarities between the two classes. The best MLP model could not exceed 69% accuracy. Due to the underfitting of the model, we decided to dial up the complexity of our chosen model and experiment with CNN models which specialize in difficult image classification. The first model yielded a test set accuracy of 66%. Tuning this model led to an accuracy of 82% and an F1 score of 84%. The next step was using one of the award-winning pre-trained model architectures. The VGG16 architecture was adopted to build a more complex model compared to our existing models. The best pre-trained model gave an accuracy of 85% and an F1 score of 86%. As shown in this slide, the CNN best model confusion matrix had the lowest misclassification rate of 15%. There were 80 sedans that were correctly classified as sedans when they were in fact sedans. Likewise, 96 vehicles were correctly classified as SUVs when they were in fact SUVs. On the other hand, 24 sedans were misclassified as SUVs when they were in fact sedans. and 7 vehicles were misclassified as sedans when they were in fact SUVs. Best chain model had the accuracy of 85%, precision of 80%, recall of 93%, and F1 score of 86%. As shown in the learning curve below, the accuracy of the best model is gradually increasing for the training set, and similarly the validation set accuracy was following the trend closely. The validation curve for the best model appeared to be following the training curve, leaving a small gap between both the curves. This indicates that we did not encounter any overfitting problem with the best model, and that according to our validation curves, this model appeared to be generalizing well. This project tackled the first level of complexity for a car classification problem. These are few recommendations. A first step would be to increase the amount of data for this model. After achieving a satisfactory accuracy and F1 score on this model, more vehicle body styles can be introduced to the model as a different classes such as trucks, vans, scoops, etc. The final step of future work would be to implement this model in a production for analyzing both live and static images. This would require the model to be integrated into an end-to-end solution software package like a website that takes live and static images, classifies, stores the proper information in the company's database. These are some references we used for our project.